The air which we breathe is also a very important industrial raw material. This is the first of two films about some of the uses of air in industry. At this BOC plant in Widnes in northwest England, air is separated into its main constituents, oxygen and nitrogen. We'll start by seeing how that's done, then look at what these gases can be used for. Here are the air intakes. 2,000 cubic meters of air a minute can be sucked in down each of these stacks. The air is filtered to remove particles of solid matter. First through coarse filters, then through finer material. This fabric was white when it was first installed. The filtered air is then compressed to 6 times atmospheric pressure. Here's one of the compressors. When any gas is compressed, its temperature rises, as you'll know if you've ever felt the end of a bicycle pump when you're pumping up a tyre. So the compressed air is now cooled by cold water. But if you take a compressed gas and release the pressure, let it expand, it loses heat. It gets colder. This effect is used to cool the compressed air so much that it turns into a liquid. The compressed air is allowed to expand in 2 stages. In the first stage, it starts at 295 Kelvin, 22 degrees C, and emerges much colder at 200 Kelvin, minus 73 degrees C. As it expands, it's made to turn turbine blades to generate electricity. It produces 600 kilowatts of electrical energy, which can be used in the plant. There's the first expansion turbine. Inside you can see the turbine, which is linked to an electrical generator. This one's not in use at the moment. A second expansion turbine cools the gas down to 120 Kelvin, minus 153 degrees C, and generates another 1,100 kilowatts of electrical energy, so giving back some of the energy used up in compressing the air in the first place. Some of the very cold air is used to freeze carbon dioxide and water vapour out of incoming air in this part of the plant. The whole plant is very complicated, but in the end, using this simple principle that when a gas expands it cools, oxygen and nitrogen in the air can be separated out as liquid oxygen and liquid nitrogen. The process goes on continuously, night and day, monitored and controlled from a central control room. To keep the liquids inside as cool as possible. This is how they're constructed. The big tank inside the outer casing holds the liquid oxygen or nitrogen. It's supported on a heat-insulating base. The space between the inner tank and the outer skin is packed with little pellets of porous insulating material, rather like cavity insulation in the walls of a modern house. This is the insulating material made of glass. A rail tanker wagon is being filled with liquid nitrogen using a pump. For an initial very short period, the liquid boils and turns back into gas as it enters the stainless steel tank. This gas is released through a valve. Because of the latent heat of evaporation, this produces extreme cold. Then, as the tank cools down, the liquid nitrogen stops boiling away. You can see ice forming on the pipework. Once again, the inner tank containing the liquid nitrogen is well insulated from the outer skin so that it doesn't easily warm up. Road tankers are also used to transport liquefied gases. Air contains traces of other gases as well as oxygen and nitrogen. At this plant, liquid argon, a noble gas, is also produced in the process and sold for use in industry. Here's one use for liquid nitrogen. Big trucks are used to transport chilled foods. They have to be refrigerated. One way of doing this is for the truck to carry its own little tanks of liquid nitrogen. The tank is connected to a length of copper piping which runs all round the inside of the truck. There are small holes at intervals along this piping. This is a heat sensing device. As soon as the temperature inside the van reaches a certain level, a valve opens automatically and releases liquid nitrogen into the pipe. As the liquid silently evaporates, turns back into a gas, it cools the interior down until the heat sensor signals to the valve to shut off again. In this way, the chilled food can be kept cool, and because nitrogen's a very unreactive gas, it cannot in any way cause damage to the foodstuffs. An empty truck backs up against the cold store, where chilled food is held for a short time before it's sent out to the stores. Chilled food will only keep fresh for a short while, and the delivery system has to be well organised so that the products arrive in good condition for the customers. Frozen foods, another very important use for liquid nitrogen. This is sliced turkey. It's covered with batter, then breadcrumbs, then fried. The cooled products pass into a freezer tunnel. Food can be frozen by having liquid nitrogen sprayed directly onto it. They open the side so that we could see what happens. Once again, remember that nitrogen is very unreactive, so it cannot harm the food. And out it comes, deep frozen, ready to be wrapped, and eventually to find its way into home freezers. Here's another unexpected use for nitrogen. Bags of crisps can be filled with nitrogen. This helps preserve freshness, and at the same time the crisps are cushioned when they're stacked or handled. Let out the nitrogen from these bags, and the weight we put on crushes them into little pieces. Sometimes the oxygen and nitrogen gases produced at liquefying plants are sent directly to nearby customers along pipelines. Here at Middlesbrough, the plant supplies many big industrial customers. Oxygen is used, for example, to enrich the air blown into blast furnaces to produce iron. And oxygen is also used in the basic oxygen steelmaking process, as you can see in another of these chemistry in action films. Producing cheap and plentiful oxygen and nitrogen out of the air through liquefaction is In fact, a special burner has to be used at the plant. The liquid sulphur comes out through the holes inside this big rotating cup, and as the cup spins, it's spun out around the inside, like this. When it reaches the rim, the liquid sulphur is broken up into tiny droplets by air blowing out through this circular slot. The tiny droplets burn very rapidly in the air inside the big box in which the burner is fixed. "11 tons of liquid sulphur an hour are burned inside this combustion chamber, using 70,000 cubic meters of air an hour. Sulphur burns in the oxygen of the air to produce SO2, sulphur dioxide. More air than is needed goes into the burner, and the mixture of sulphur dioxide and this excess air is now passed into a converter where another reaction occurs. Here's a lab demonstration. Sulphur dioxide comes from this cylinder, and we've also got oxygen. The gases are dried by passing them through concentrated sulfuric acid. They then pass over a heated catalyst. It contains platinum, and these dense white fumes are produced. Here's the reaction. In the presence of the catalyst, the sulphur dioxide reacts with oxygen to produce sulphur trioxide. This reaction goes on here in the industrial plant. The catalyst used contains a compound of the element vanadium plus certain other substances. It's mounted on these porous rings, each of which has a very large surface area because of the little spaces inside the rings. The reaction takes place on these surfaces. Back to the lab. If we pass the issuing gases into a tube cooled in an ice and salt freezing mixture, solid sulphur trioxide is produced, the white substance you can see. If we add water, there's a dangerous, vigorous reaction, producing a lot of heat. Divide the solution produced into 2 portions. Add blue litmus to one portion. What does this tell you? To the other portion, we add dilute hydrochloric acid. Followed by barium chloride solution. This shows what's been formed. Sulphur trioxide reacts with water to give sulfuric acid. And a lot of heat. Industrially, the sulphur trioxide isn't passed straight into water. Instead, it's passed into 98% sulfuric acid, in which it dissolves. The water present then reacts with this dissolved sulphur trioxide to make more sulfuric acid safely, without a high temperature being produced. The sulfuric acid made at the plant is stored in steel tanks until it's loaded into stainless steel road tankers for delivery. They can't start to fill the empty tanker until the barrier has been dropped, because the key is needed to start the operation. Safety barriers are fixed to the side of the vehicle. Another product can be made from the sulphur trioxide produced at the plant. In these tanks, molten sulphur is run into a solution of sulphur trioxide, and the gas sulphur dioxide bubbles off. Here's the equation for the reaction. Sulphur trioxide plus sulphur gives sulphur dioxide. The process can be watched using a closed-circuit television camera, which shows what's happening on a screen in the main plant control room. The sulfur dioxide produced is liquefied and transported to wherever it's needed. Sulfur dioxide is used to make a number of other industrial chemicals, and also, as you can see in another of these films, to remove the excess chlorine from water that's been treated at water treatment works. The waste gas emerging from the sulfuric acid plant is mainly nitrogen from the air drawn in at the beginning of the process. There are traces of other gases, and these are analysed to make sure that only very tiny amounts of sulfur dioxide get out into the atmosphere. In the control room, the whole process is monitored continually. The plant produces about 33 tons of sulfuric acid an hour, running continuously day and night. Samples of the product are tested. Electrical conductivity measurements show its concentration. There are many uses for sulfuric acid: making titanium dioxide pigment for paints, making fertilizers, making detergents. Here at the Rock Savage plant, much of the acid is used to produce. If you heat calcium fluoride with concentrated sulfuric acid, the gas hydrogen fluoride is given off, which forms the very dangerous and corrosive hydrofluoric acid with any water that's present. It's done on an enormous scale industrially, in huge rotating kilns. Everything inside is completely dry, and under these conditions, the hydrogen fluoride doesn't attack the steel which the plant's made of. But the operator taking off a sample for analysis has to wear full protective clothing so that he's not exposed to the fumes coming off and doesn't breathe them in. The dry liquefied hydrogen fluoride is stored, taking all precautions. It's used to make certain carbon compounds containing fluorine, which are very stable and non-poisonous, and are used in refrigeration, and also as propellants in aerosols. These fluorocarbons, as they're called, are relatively harmless if they're breathed in. Making hydrogen fluoride is only one of the many uses for sulfuric acid. Throughout the world, sulfuric acid is produced in enormous quantities in big chemical plants, such as the one we've seen. It's one of the most important chemicals made, using the air around us as one of the raw materials.